Right, folks, question 5. I'll do 2 questions this time, question 5 and 6 all in one go, I think. You have to talk about the elements of group 1. In your GCSE, you need to know about elements in group 1, elements in group 7, elements in group 8 or 0, which is the noble gases, and the transition metals. This is just one about group 1. So potassium, rubidium added to water. You're only expected to know in detail about lithium, sodium, potassium and predict what would happen with rubidium. But you know the reactivity increases down the group, I think. And most of you realise then that as you go down the group, therefore you'd see a more vigorous reaction. So it might be more vigorous bubbling. You have to be really clear there, but it's more vigorous bubbling rather than just vigorous bubbling, because you get vigorous bubbling with potassium too. So more vigorous bubbling, or a brighter flame, or it catches fire more quickly, or it moves around more quickly, or disappears more quickly, or melts more quickly. But the whole idea is that it's more vigorous, faster reaction because it's more reactive. And we then have to explain why it's more reactive. And you know, there were some really excellent answers in this, I would say. But the key thing to remember is they both react by losing one electron because they're both in group 1. They both have one in the outer shell, and as we said in the previous question, they tend to react. Elements tend to react to end up with a full outer shell, right? So why does rubidium react more quickly? Well, its electron is less tightly held to the nucleus. There's a better way of putting that though, isn't there, which gets the mark. So let's go through the kind of mark scheme. So the reason why it's less tightly held is that rubidium has more shells of electrons, but really that means that the electron is further from the nucleus. So outer electron further from the nucleus. Right, so you can't get 2 marks for saying those 2 things, it's kind of one or the other. So the fact that rubidium's larger, the electron's further away from the nucleus, means that the electron is less tightly held, because force is proportional to, for those of you who really want to get into this, force is proportional to 1 over the distance squared, the force of attraction there. Anyway, that means there's less electrostatic attraction. So less electrostatic attraction. I wanted you really to be talking about electrostatic attraction if you want to get a really good understanding between the electron and the nucleus. And therefore it's lost, the electron lost more easily. Now some of you did a nice job of talking about more shielding, and that was a good alternative to the second point. So they allowed more shielding instead of less electrostatic attraction. It's not a required knowledge at GCSE, but it's nice if you know that the inner electrons shield the outer electrons from the nucleus, and also mean there's less electrostatic attraction, the electrons lost more easily. You might have worded this even more nicely by saying less energy is needed to remove the outer electron as an alternative to this as well. Now, question 5.3 though was a bit of a disaster, I would say. Right, so these are the alkali metals, group 1 of the alkali metals, and you all know that alkali means, oh, well, most of you know that alkali means OH minus. So the product must be rubidium hydroxide. Hydroxide is a 1 minus ion, rubidium is a 1 plus ion, so rubidium hydroxide must be RbOH. It had to be that, and that would get a mark. Very few people actually got that. You came up with rubidium oxide of various forms. Many of you knew that alkali metals fizz when they go into water, and that fizzing is hydrogen. You get a mark for that. And then you had to balance. And I'm just going to walk you through balancing an equation if you don't know what to do. So you count the rubidiums, the hydrogens and the oxygens on each side. Rubidiums, hydrogens and oxygens. On the left there's 1, and on the right there's 1. Hydrogens, you've got 2 there, because the 2 obviously comes after the hydrogen. And on the right you've got 3, and on the left you've got 1 oxygen from the water, and on the right you've got 1 from the hydroxide. So we're short of hydrogens, so we need to have more hydrogens, so we stick a 2 in front of there. Gives you 4 hydrogens and 2 oxygens. So we now need more hydrogens and oxygens on this side, so we must have one more rubidium hydroxide. We've got a 2 there, 4 there, and a 2 there. To balance up the rubidiums, you do that. Okay, so that's an equation worth learning, or certainly being able to work out. Very, very common that comes up. That's the 3rd mark for balancing. Okay. So question 5.4, there was a multi-choice at the top. This was done pretty well. So the noble gases, you should know that the boiling points increase down the group. So that's that mark. The reason the top one's not right is that helium only has 2 in its outer shell, remember. So that's why that one's not right. They're not diatomic. The ones that are diatomic, if you look at a periodic table, I'll just write them down there to remind you. So the diatomic, or the ones with 2 atoms, are nitrogen, oxygen, chlorine, fluorine, bromine, all the halogens, iodine, as well as hydrogen. Okay, so it's worth learning those if you don't know them. And the whole thing about noble gases, the reason they're called noble gases, they're unreacted, so it couldn't have been that one either. This question was done very well typically. I'm not really inclined to work it through on paper, but the calculation of relative atomic mass is the mass number times the abundance for each of the different isotopes. Definition of isotopes, remember, is same number of protons, different number of electrons. Same number of protons, different number of neutrons. So for each one you've got one more neutron. That times that, add that times that, add that times that. Then you have to divide by 100, which is the sum of the percentage abundances. And that comes to 20.1877. But look, if it says give an answer to a certain number of sig figs, you must give it to that number of sig figs, so that's 20.2, which is the right answer there. That was well done, typically. Next question about electrolysis was relatively tough. It's a bit different to the process that you've seen in the lab. It's not the same. You should expect this in your GCSE paper. So you should expect to see things you haven't seen before. You have taken sodium chloride solution and done electrolysis. But when you do electrolysis of molten compounds, molten ionic compounds, you get the elements produced. So you should realise you get sodium chloride turning into sodium and chlorine, and if I had to balance that, it would look like that. If you do that, you've got to heat up the sodium chloride solid to make it a liquid. The chlorine gas will be produced at the positive electrode, and the sodium will be produced at the other. Okay. Turns out the molten sodium would float on the top because it's quite low density, and you'd be able to draw it away through this pipe, and the chlorine gas, of course, would disappear up there. So, what's going on then? So, in this reaction, or in this process, in sodium chloride, you've got sodium ions and chloride ions. That's what sodium chloride is. It's an ionic compound, right? So, when sodium forms from sodium ions, it must be that those sodium ions turn into atoms. So it had to be either of these two answers. Sodium atoms turn into sodium ions turn into sodium atoms. They do so because a sodium ion has only got 10 electrons and a sodium atom has got 11 electrons. It must be this process where sodium atoms are formed from sodium ions and 1 electron, so that's the process. If the sodium ion lost an electron, which is what's going on in this one here, you'd end up with a 2+ ion, so that can't be right. Right, so in the next question it's asking, why must you keep the products of the electrolysis apart? Notice in the picture, the sodium and the chlorine are kept apart from each other. And most of you realise that they're both very reactive elements, and the reason you keep them apart from each other is to stop them from reacting. To stop Cl2 and Na reacting. They'll react very vigorously. It's reacting. Yeah. And the particle that passes through the mesh in the electrolysis kit was one that was actually done pretty well, I would say. Most of you realise there must be ions moving through, because you know that ionic compound, the only thing that flows with ionic compounds is ions, so it must be ions travelling through the mesh there. Okay, and that's the answer. So again, that mesh is to stop the chlorine and the sodium interacting with each other. Right, if you take aqueous sodium chloride, things get a bit more complicated. You get two gases. You're told in the question you get two gases and an alkaline solution then. Right, so what's going on? In aqueous sodium chloride, what that means is it's dissolved in water. The water is a substance which mostly exists as drawn as H2O, but ever so slightly, a bit like a very, very weak acid, partially dissociates into hydrogen ions and hydroxide ions. It's well over 99.999% of this stuff and a tiny amount of this stuff, but there is a little bit of that in there and that in there, and that's important for electrolysis in aqueous solutions. So the answer here was hydrogen ions and hydroxyl ions. You could have written the word or simply drawn the symbol as I've done there. Right, so you then asked what solution is produced, and it's an alkaline solution, so it must have been hydroxide. And so what metal must it have been with? Well, it's only sodium you've got there, so it was sodium hydroxide. Alkaline means hydroxide, and so it had to be sodium hydroxide. But you have to explain that, and I'm going to do that now, referring to the processes at the electrode. So I'm going to draw a little diagram to help you see what's going on. I'll walk you through the mark scheme. Many of you got 1 mark here. Very few people got more than 1, and lots of you got 0 as well. Okay, this is obviously a difficult question, and if you read the examiner report, lots of people found this very difficult, so don't worry. So here's electrolysis going on, or electrolysis kit. That's the positive electrode, that's the negative electrode, and you've got aqueous sodium chloride in this pot. This is the electrolyte. Okay, so in that pot you've got sodium ions and chloride ions. Now when sodium chloride is dissolved in water, they're not attached to each other in those lattice structures. There's trillions of these things whizzing around in solution. The sodium ions are heading to the cathode, the negative electrode, and the chloride ions are going to the anode, the positive electrode. But remember, there is also a tiny amount of hydrogen ions in there as well, and hydroxide ions in there as well. Okay, so what's going on? Well, the cathode is negatively charged, so both the positive ions will travel to that cathode, or be attracted to that cathode. So they go over there and that goes over there, and likewise the negative ions are both attracted to the anode. So then it's a competition. Only one of these can be reduced. Only one of them can pick up the electrons needed to turn it into the element. And you're expected to know that if the element in the ionic compound, in this case sodium, is more reactive than hydrogen, then that will stay in solution, because more reactive things love being ions, and low reactivity ions like copper, for example, would prefer to be elements if they possibly can be. But in just about every case except copper, the element is more reactive than hydrogen, so that stays in solution, and the hydrogen ions get what we say discharged. So the hydrogen ions turn into hydrogen atoms, but hydrogen atoms don't exist on their own. As soon as they bump into each other, they form a covalent substance H2. So it must be that 2 hydrogen ions have been reduced with 2 electrons. So that's the half equation that's gone on there. Okay. At the other electrode, you've got a choice of chloride or hydroxide that are discharged. and you're expected to know the reasons why are fairly complicated, and we cover them in year 13. But it just so happens that the chloride is oxidized preferentially, and you're expected to know that. If you've ever got a halogen in solution, it will be discharged or oxidized, and that gives you chlorine, and that's the half equation. So the chloride ions each lose an electron to make chlorine atoms, which combine to make chlorine molecule, and there are the 2 electrons that have been lost, one from each chloride. So what you left, so if the chloride ions have been used up and the hydrogen ions have been used up, you're left with sodium hydroxide. So that's what the 3 marks are: sodium and hydroxide ions left in solution, and that would then give you a pH of 14. So pH greater than 7, certainly be very high, something like 14. Okay, so why? And you get a mark for saying hydrogen ions were reduced or simply discharged. Discharged means no longer have a charge, turn into atoms, and the chloride ions were discharged or oxidized. And that's what the marks are for. And I thought that was a really tough question to get the marks for. Okay, there we are. That's the answer to that one. Is that it for that question? Looks like it might be. Right, in that case I'll stop.